Okay, this is going to be the asynchronized lesson, or the pre-recorded lesson for 9BR week 3, period 4. And we're going to try and squeeze a lot into this lesson. So we'll see if it's one part, or it might have to be done in multiple parts, maybe 2 or 3 parts. We'll see how it goes. So first of all, I want to go through how to use the melting point and boiling point of a substance to determine whether it's going to be a solid, liquid or gas at room temperature. As you know, there are many different types of substances. Some of them are solids at room temperature, some of them are liquids at room temperature, and some of them are gases at room temperature. So for a minute, just try and think about some different substances. For example, the common gases in the air, nitrogen, oxygen. These are all gases. They're found in the air, and they're gases at room temperature. Other substances are liquids at room temperature. For example, water is a liquid at room temperature. For example, petrol is a liquid at room temperature. For example, oil, and so on and so forth. And then there are substances which are solids at room temperature, like most metals, the exception being mercury, and many other substances solids at room temperature. So what is it that makes these different substances different states of matter at room temperature? First of all, you have to know what room temperature is. So room temperature is approximately 25 degrees C. Okay, now we say approximately because it depends on the room, really. Okay, some rooms are slightly warmer than others, some are colder, depends if you've got the AC on, and so on and so forth. So we can regard, for the purposes of questions and calculations, room temperature as about 25 degrees C. Okay, but beware, with certain types of questions, you have to check what the initial starting temperature was. So even though it might have been done at room temperature, the initial temperature or room temperature in that particular question might be slightly different. There's some questions where the initial temperature is 24 or 23, okay, sometimes 25, sometimes 26, okay? So you have to check the question if it's that type of question. But for this purpose, we're going to use 25 degrees C as room temperature. So what you need to do is look at the melting and boiling point. Remember, melting point is the same as the freezing point, okay, and the boiling point of the particular substance. For example, let's look at water. Okay, water has a melting point, which is the same as the freezing point of 0 degrees C, and a boiling point of 100 degrees C. So, where does that fit in relationship to room temperature of 25 degrees C? Now, a substance is going to be a solid if its melting point is, try and think about the answer. A substance is going to be a solid when a substance is going to be a liquid when a substance is going to be a gas when. So, a substance is going to be a solid, I don't know if you've managed to work it out, if its melting point, and naturally, by the way, the boiling point is always going to be higher than the melting point. Sometimes there might not be that much of a difference between the melting point and the boiling point. They might be quite close together. But the boiling point is always going to be higher than the melting point. So for example, if I say the melting point is higher than a certain temperature, I don't need to say the boiling point, because that's automatically known and assumed, because the boiling point is always higher than the melting point. So coming back to when is a substance a solid at room temperature? When its melting point is higher than 25 degrees C. Okay, so the melting point is greater than 25 degrees C. Right. Now, with water, let's look at water. Is the melting point higher than 25 degrees C? No, it's not. It's below 25 degrees C. So that's why it's not a solid at room temperature. Okay. Let's move on to gas. When is a substance going to be a gas at room temperature? Let's give this a little heading first of all. A substance will be, so we can make that the heading. So it's understood as follows. A substance will be a solid, so at room temperature, at room temperature. Okay, a substance will be at room temperature a solid if its melting point is greater than 25 degrees C. A gas when what? If it's a gas, then what do we need to look for in the melting or boiling point? Its boiling point is going to be less than 25 degrees C. So that, for example, let's say a substance has a boiling point of 24 degrees C. Okay, then at 25 degrees C, it already will have turned into a gas by boiling at 24 degrees C. So by the time it's 25 degrees C, it will already have boiled and turned into a gas. So a substance will be a gas at room temperature if its boiling point, let's keep the colour the same, if its boiling point is less than 25 degrees C. Okay, so what does that leave for a liquid? Now, before we go on to liquid, let's look at water, okay, to see if it's a gas at room temperature. So, does water have a boiling point less than 25 degrees C? No, 100 degrees C is more than 25 degrees C. So that's why it's not a gas at room temperature. Okay, so what does that leave for a liquid? Now there's two ways of saying it for a liquid. You can either say its melting point should be lower than 25 degrees C, but its boiling point higher than 25 degrees C. That's one way you could say it, and if you prefer that, then that's what you can write down. But some people prefer saying that a substance is going to be a liquid at room temperature if 25 degrees C, meaning room temperature, is in between the melting point and the boiling point. Okay? Some people prefer to look at it that way. So that's what I'm going to write down. But if you prefer to say once more that the melting point is below room temperature and the boiling point is above room temperature, then it's going to be a liquid. If you prefer that, no problem. That's what you can write down. If you want, you can write both down. So it's a liquid if room temperature, which is 25 degrees C, is in between its melting point and boiling point. Okay, it's a bit squeezed in there, but I think you can see that. All right, so make sure you get that down. That's how to determine whether any substance, as long as you know its melting and boiling point, you can determine whether it's going to be a solid, liquid or gas at room temperature. Okay, the next part of the lesson is to do the Bunsen burner. So that's the first part done. The second part is to do with the Bunsen burner. Bunsen is the name of the person. Burner. So what you need to do is to be able to identify different parts of a Bunsen burner and to know the differences between the two types of flame and what they're used for. Okay, now before we go ahead, you will never be asked to draw a real Bunsen burner in an exam question. Okay, you won't be asked to draw it. The only thing that you'll be asked to do is an arrow with heat written under it. That's what we use to represent a Bunsen burner. So for example, if you have a tripod and a gauze and you've got a beaker on top with some water in it and you're heating it with a Bunsen burner, you never draw the Bunsen burner in chemistry exams. You never draw the Bunsen burner. You always use an arrow with heat to represent a Bunsen burner. However, there are some questions, usually in paper 6, where they bring you a diagram of an actual Bunsen burner or other piece of equipment like this, and they'll ask you to label. Okay, so you need to know that this, for example, is a beaker, this is a tripod, this is a gauze, and so on. And they'll draw a Bunsen burner, for example, a proper one, and you'll be asked to label it. So you do need to know what it looks like, but you won't have to draw it yourself. Okay, so what does the Bunsen burner look like? Here are some photos of a Bunsen burner. Okay, there's some photos of a Bunsen burner. Okay, so what you need to know are things like the main parts. So this here at the bottom is the base. You've got the tubing which provides the gas supply, okay, for the fuel to burn. You've got the air hole, that's very important. Notice the air hole. And then it's got like a sleeve or a collar around it which can be turned to close the air hole or to open it. And then the main chimney and then the flame at the top. Okay, so they're the different parts. Now, when the air hole is open, it gives a certain type of flame, and when it's closed, it gives a certain type of flame. So you need to know what type of flame you get with what air hole. Is it open or is it closed? So the two types of flame are the yellow flame and the blue flame. But these also have other names. These types of flames also have other names. So, for example, the yellow flame is also called a safety flame, or a standby flame. Okay, and the blue flame is also called a heating flame or a burning flame, or sometimes a roaring flame because it makes a roaring noise. Okay, the safety flame or standby flame is silent, you can't hear it. So these are the two types of flame. Now, as I said before, when you turn that sleeve or that collar around the air hole, you can control whether it's open or closed. This is when it's closed, okay? You get this yellow flame. And this is when it's open, you get this blue flame. So what are the two types of flame for? Well, as you can see from the name of the type of flame, safety or standby flame, you never use the yellow flame for actual heating purposes. You use it just to put it on standby while you're doing something else, you know, so that you don't have to turn it off and then relight it, which takes a lot longer. You could just turn it on standby, okay? And the reason it's called a standby or a safety flame is for two reasons. One, it's very visible, you can see it clearly, okay, even from a distance in the lab, so that you don't go near it by accident. Secondly, it's a lower temperature flame, okay? The flame is at a lower temperature, so it's not going to cause as much damage as the blue flame, which is at a higher temperature. Okay, so the blue flame is actually used for heating or burning substances, and you know, it's also called a roaring flame, but you mustn't just leave it on that flame when you're doing something else, like when you're in standby mode, because number one, you can't see it clearly. It's almost invisible. So it's very easy that, you know, you might accidentally come into contact with it or get too near it without realizing that it's on. And number two, obviously, it's a much hotter flame at a higher temperature and can therefore cause more damage. So you never use one for the other purpose. You never use the safety flame for heating or burning substances, okay? If you heat something, for example, in a beaker with a safety flame, the bottom of the beaker is going to turn black, okay, because of the unburnt charcoal. The unburnt soot and carbon, which is released by the yellow. Sometimes they even call it yellow smoky flame because it gives off smoke as well, okay? And like I said, you never use the heating or burning flame or blue flame for standby purposes. Right, the final thing about the Bunsen burner that you need to know is why does the closed air hole produce the yellow flame, and why does the open air hole produce the blue flame? Now, we haven't done fuels yet, but when we get to the fuels topic, you'll come across something like combustion, okay? You'll come across a type of reaction called a combustion reaction, where a fuel burns in oxygen, okay? A fuel burns in oxygen and releases heat energy. And this is exactly what's going on here. So the fuel which is coming in through this rubber tubing here and here is coming into contact with oxygen from the air, which comes in through this air hole, okay? And it burns, releasing obviously heat energy. But there are two types of combustion. One is called incomplete combustion, and the other is called complete combustion. Now, when do we get what type of combustion? Complete combustion happens when there is a plentiful supply of oxygen. So when the air hole is open, there's plenty of oxygen that is reaching the fuel, and you get complete combustion, okay? And the products, when the fuel is for example, methane gas or a hydrocarbon gas like it is here, then the products are going to be carbon dioxide and water vapor. Don't worry too much about remembering that because it will come up again in the fuels topic, okay? But here, just notice the differences between the two types of flame and what causes that. And incomplete combustion, on the other hand, happens when there is insufficient oxygen, when there's not enough oxygen. Okay, so that causes incomplete combustion, and one of the products that form with a carbon-containing fuel are carbon monoxide and water vapor. And that's why with incomplete combustion you get this yellow smoky flame, because the fuel does not burn completely. Okay, so some of the fuel remains as unburnt carbon, and it produces that ash and that smoke and that soot. And that's what you need to know basically about the two types of flame and a Bunsen burner. You need to copy this information from what I've just explained, using whatever diagrams you want to from the internet. If you prefer, you could use this diagram itself. It's a little bit blurry in places, but you could use that diagram or another diagram of your choice of the Bunsen burner, and an explanation according to what I just said. You need to transfer that into your notes. Okay, the third and last part of this lesson is to do with separation techniques or purification techniques. And there are about 8 or 9 that you need to know. Obviously, it's going to take some time to go through them all, so we'll just try and go through 1 or 2 today for this lesson. So the first one is called filtration. Okay, and these headings are extremely important for each one. Let me just give you a preview of what's coming up. So filtration is this one. Okay, and then you've got evaporation. Then on the next page you've got crystallization. We don't have a separate diagram for crystallization because it's almost identical to evaporation. It's very, very similar to the previous one of evaporation. So evaporation and crystallization are very similar. And then you've got simple distillation. And then you've got fractional distillation. And again, they look very similar, but there are important differences between them. And then you've got separating funnel for separating another type of mixture, and chromatography. And then there's one more which we're going to add at the bottom there, which we've already come across, but we'll deal with that later on. So let's go back to the first one, filtration. So as I was saying, the titles are extremely important because the title tells you what type of mixture can be separated using that technique. All right, and you have to learn these properly, otherwise you're not going to know what type of technique to use with what type of mixture, and vice versa. All right, so filtration is used to separate an insoluble solid from a liquid or a solution. So now the question comes, well, how do I know what type of solids are insoluble and what type of solids are soluble? Okay, and the answer to this question is not very simple. Okay, the answer is not that straightforward and simple, because some of those substances just from your common life experience and your experience from earlier grades. Okay, for example, the salt that you put on food that you eat, sodium chloride. Can you tell me if it's soluble? And when I say soluble or insoluble, I mean in water, unless it's specified otherwise. So sodium chloride, is it soluble or insoluble? Most of you probably know that it's soluble in water. You can get some salt, you can put it into a glass of water, and if you stir it, it's going to dissolve. Okay? Likewise, sugar. Is it soluble or insoluble? And most of you know that it is in fact soluble. Okay? And then there are other substances as well that you might have come across in earlier grades, like for example, a substance called limestone, or marble, as it's also known. Okay? Or chalk, as it's also known. And its actual formula is CaCO3, and its proper chemical name is calcium carbonate, right? Calcium carbonate. So, is this substance soluble or insoluble? Like I said, you should have come across it in earlier grades. But if you didn't, no problem, because I'm going to tell you everything you need to know, right? So, limestone or calcium carbonate is actually insoluble in water. Now, in a few pages' time, in the next topic, actually, you're going to come across a certain general rule or certain general principle, which you also might have heard of before, which is that ionic compounds are soluble in water. Okay? Now that's true in general, but there are exceptions. So how are you supposed to know the exceptions? Well, you don't need to know all of them, but the ones that you do need to know can be found on page 89. So these are the ones that you need to know. Okay, because remember, ionic compounds are generally soluble in water, but these are the ones which are insoluble. For example, amongst the chlorides, iodides and bromides, they're mostly soluble, but the ones which are insoluble are silver chloride and lead chloride, and likewise silver bromide, lead bromide, silver iodide, lead iodide, right? So from the halides, they're generally they're generally soluble. Okay, from the halides, they're generally soluble, but these are the notable exceptions that you need to know: silver halides and lead halide. So silver chloride, lead chloride, etc. Now the next one is from the sulfates. Okay, from the sulfates. So the sulfates are mostly soluble. The ones which are insoluble that you need to know are barium sulfate, calcium sulfate, and lead 2 sulfate. Okay? And then likewise, so and so forth for the rest of the table. Nitrates are nice and easy to remember because all nitrates are soluble. Nice and easy. All nitrates are soluble. You don't need to worry about any insoluble exceptions. Okay? Another useful one to know is all sodium compounds are soluble. All sodium compounds. So whenever you come across a sodium compound, then you know it's going to be soluble, right? And likewise for potassium compounds and ammonium compounds, right? And then you got some, for example, like the hydroxides, which are generally insoluble, all right? They're mostly insoluble, but the soluble ones are mentioned here. These are the ones you need to know, the soluble ones. There are also other soluble ones, but you don't need to know them. In other words, they'll tell you in the question what its state of solubility is. Okay. So, that's important to have a look at page 89 to determine what is soluble or insoluble. And obviously, you're going to have to learn it at some point. So, separation of an insoluble solid from a liquid or a solution. Now, filtration is the name of the technique. filtration, not filtration. Okay, filtration. Let me just rub this out to make a bit of space. Okay, filtration, not filtration. And then it mentions something called decanting. Now, decanting sometimes causes problems for students because even though I warn them not to use decanting to answer a question unless you've got no choice, you always get those students who either don't pay attention or want to do what the teacher has told them not to do. Okay? And that's a surefire way of losing marks. So I'm telling you again, as I always tell my students every single year, do not use decanting instead of filtration unless you have no choice. For example, if the question says, other than filtration, describe a way of separating an insoluble solid from a liquid, right? So there you've got no choice because they said other than filtration, right? The reason why I'm saying this is because decanting doesn't work in every situation of separating insoluble solid from a liquid. No. Decanting has a very important condition in order to work. A very important if. This if is very important, right? If the solid is heavy and has settled. So, for example, imagine a beaker of water. Imagine a beaker of water, and at the bottom you've got some stones or big pebbles, right? The pebbles are heavy, and so they've settled to the bottom. And the meaning of decant is, can anyone tell me the meaning of decant? The meaning of decant is pouring off the liquid carefully, leaving the heavy, settled solid behind. Okay? And you can write the meaning of decant here. So that's the meaning of decant. Okay, make sure you copy that down. Let's just highlight that as well there. And you can highlight the meaning of decant. Okay, so that would work in this scenario of a beaker of water with some pebbles or stones at the bottom, which are heavy enough to be settled to the bottom. So you can gently pour off the liquid, okay, by tilting the beaker gradually and gently, leaving the stones at the bottom. That works in this case. But what about with substances that do not fully settle to the bottom? Okay, for example, a lot of students make mistakes on this one, where the question is asking, how would you separate sand from water? And instead of saying filtration, like they should, like they've been told to in class, and like I'm telling you again here, okay, instead of using filtration, some students will say decanting. And when I ask them, why did you choose decanting when I told you to use filtration? They'll say, because the sand is heavy and settles to the bottom. And I'll say, no, it doesn't. Not all of the sand is going to settle to the bottom. Sand is not something which is uniform in size and shape and mass. Some of the particles of sand are heavy and yes, will settle to the bottom. But some of the particles of sand are very fine and very light and very small and take time to settle to the bottom, okay? So they will remain suspended and floating in the water. So when you go to pour off that mixture, that liquid from the sand, some of the sand is going to pour off along with the water and you're not going to get separation. That's one example. Another example, which I want you to think about now, is separating tea leaves from tea. Not a tea bag, tea leaves. Imagine you've made a cup of tea using some actual tea leaves. Okay, so you've brewed the tea's dissolved, you're ready now to separate the tea leaves. Now, of course, the best thing to use would be filtration, okay, where you've got filter paper as shown in this diagram. There's a filter funnel. You pour the tea and the leaves mixture here in at the top. The leaves get trapped by this filter paper and the tea drips through the filter paper and is collected in a beaker or suitable vessel, okay? And the tea drink here would be called the filtrate. We'll go through the labels in a bit. So that's what you would use. But my question is, could you use decanting? Could you gently pour off the liquid tea whilst leaving the settled tea leaves behind? I want you to think about that question, think about the answer, pause or, freeze the video if you need to. And the answer is that no, you should not use decanting. Because while some of the heavier leaves will settle to the bottom, not all of them are the same. You get small pieces of tea leaves which are going to remain floating at the top of the mixture. And so when you try and pour the tea off, some of those leaves are going to pour off along with the tea. So you're not going to get separation. So this is what I mean. Don't take the risk. Yes, you have to understand the meaning of decant, but it does not mean you have to use it to carry out the separation when you have filtration as an option. Okay? I hope that's clear because, like I said, every year I go through the same thing, explain the same thing, okay? But there's always a handful of students in every class that will completely ignore or forget what I said, and instead of using filtration, they'll use decanting, and they'll lose the marks, and then they'll wonder why. All right? So pay close attention to that point that I mentioned about the difference between decanting and filtration. Okay? So now, what I want you to do, again, you can pause the video and you can go off and do a little bit of research in your textbook or on the internet and try and find the rest of these labels. Okay? Try and find the rest of these labels and then come back for the answers. Okay, so now for the answers. Let's find a different colour. I'm gonna use this green colour. Right. So let's start on the left hand side and go clockwise round. So here on the left hand side, you should have found that this part here is called a retort stand. That's its proper name, retort stand. Okay, you could get away with just calling it stand. Okay, but it's better to call it by its proper name. Retort stand. Now, sometimes they might label them separately, sometimes together. Okay, doesn't matter. Make sure you know which part is which. So that's the retort stand, and this part, which secures itself onto the stand and onto the object on the other side, okay, is called a clamp. It's called a clamp. So together they're called the clamp and retort stand. And I'm going to show you actual photographs of equipment on another occasion. All right? I'll show you actual photographs of various bits of laboratory equipment and apparatus on another occasion. I think for today this lesson's going on quite a while. I have to try and keep it to 30 to 35 minutes or so. So let's go through the rest of the labels. Now, like I said, you pour the mixture of your insoluble solid and liquid into the top of the filter funnel where the filter paper is. And so this is called the filter paper. That's the filter paper. Obviously, this is the mixture. Yeah, this is the mixture that you've poured in. But that doesn't have a separate, label to it. That will normally be given to you in the question. Right, now this substance, the insoluble solid, which is trapped in the filter paper, that's called the residue. Okay, and then this is called the filter funnel. Notice, by the way, you don't have to have arrows. It can just be the line. But the line or the arrow must be touching the objects that you're labeling. It must be touching. Okay? For example, if you want to label the filter funnel, it can't be like this. It can't be like this, where there's a big gap between the funnel, or even a small gap. There can't be any gaps. Otherwise, you're not really labeling the filter funnel. You're labeling the air around the filter funnel, and you will lose a mark for it. Okay? So be very careful about that point. Make a note of it if you want to. So that's the filter funnel, and then you've got obviously a beaker here. That's a beaker, and this is called the filtrate. That's its general name. Filtrate, not filterate, filtrate. Okay? Now, obviously the filtrate, the actual filtrate, is going to depend on what you're filtering, right? So if you're filtering sand from water, the filtrate is going to be the water. If you're filtering tea from tea leaves, the filtrate is going to be tea, and so on and so forth. Okay? And that's basically the labels. There is one other thing which I just want to point out. I might need to go on to another diagram to show you that. Let's see if I can find... Yeah. See here, this is not an intentional mistake, but it is obviously a mistake. Alright, where there's actually two mistakes. Okay, one is that there's a gap here, which I told you should not be there. There should be no gaps. Okay, the label should be touching the item. Label should be touching the item. The other mistake, which is more serious even, or just as serious, is that there's a gap. There should not be any gaps in those types of pieces of apparatus. Okay, otherwise, if there's a gap, then the substance inside is going to escape, or it's going to leak, and it's going to pour out, and so on and so forth. That's what it means. So be careful of gaps. Make sure you don't leave gaps where there shouldn't be, and make sure that the labels touch the exact thing that you're labeling. And I'll give you an example just to illustrate why that's so important. Find a little bit of space on the side. Okay, let's say for example you are drawing a plant cell. Okay, you're drawing a plant cell, and the outside part is called what? The outside part is called the cell wall, isn't it? Right? Now, that could be the cell wall, or that could be the cell wall. They're both the cell wall. But what if you accidentally made it go too far and touch that? Would that still be the cell wall? No. Because that is now the cell membrane. Right? That's the cell membrane. And what if you made it go too far inside? Now you're going into the cytoplasm. Do you understand? So what you actually touch with your label makes a big difference. Okay? As you can see from what you already do in biology when it comes to labeling parts of a cell. Okay, so don't be surprised when you have to also do it for chemistry. And that will do for this lesson.